Hello students, welcome back to your class on mass storage structure. Last class we had addressed to the concepts of your hard disk, what is the structure of your hard disk and what are the various storage medium that is available. We also saw to the various storage infrastructures. And to the end of the session we had addressed to your disk scheduling, and in that we had addressed to three algorithms, that is first come first serve, shortest seek time, and then your scan. Now let us see the other algorithms that is there, and also we will be seeing to the disk management. So continuing with it, the next algorithm we have is the C-scan algorithm. So C-scan algorithm is a variation to the scan algorithm that is there. So this algorithm came into picture to provide a uniform wait time. In the last algorithm we discussed, if at all the head passes and then if it has to, and if there is a request that is coming after the head has passed, so that request have to wait until the read write head comes back. So the wait time was not even, it was more for some, it was less for other few requests in the queue. So here the technique is, in the scan the technique was in the direction the head movement is, if the direction is from 0 to 199, it is going to satisfy all the requests from 0 to 199, and again the read write head is going to satisfy all the requests from 199 back to 0. But the variation here is when the head reaches the other end, that is when it reaches the end, the 199, it immediately returns to the beginning of the disk without servicing any request on return. That is, it is going to start again from 0. So it is not going to satisfy any request during the return. So for the same example, the head starts at 53 and from 53 it is moving, the read write head is moving in this direction, that is towards 199. So it satisfies 65, 67, 98, 122, 124 and then 83, and previously it was again satisfying anything on the request here. Now it is directly, you can see there is no request that is satisfied, it goes to 0, and again it is starting from 0 and it satisfies 14 and 37. So the total number of head movements in this case is 382. The next algorithm that we have is look scheduling algorithm, but here I have taken the example of CLOOK. We have look as well as CLOOK. These scheduling algorithms are a different version of scan and C-scan respectively. The look is a version of scan and CLOOK is a version of C-scan. Now what is the difference between look and scan? In scan, what happened, the read write head would move from the one point to another. that is from 0 it could move to the end, that is 199, and from 199 it could move to 0. But in case of look, the arms are going to go only as far as the final request in that direction. You can notice here, even if there is any request or not, you can see here 183 is the last highest request that we have, but still the arm goes up to 199, and here also the arm goes up to 0. But that's not the case with your look. You can notice here the arm goes only up till the final request in any of the directions that is taken. So what happens in scan? It is going to satisfy the request while it is going and while it is returning back as well. The look also does the same. It is going to satisfy the request while it is going and while it is returning, but the head moves only till the final request. It is not going to go beyond that. And in case of your C look, C scan is going to go till one end and it is going to return without satisfying the request. It starts from the 0 again. The same thing happens with the C look, but it is not going to start from the 0. It is going to start from the request that is available on that side. So you can see here, it is 53 is the head start, 65, 67, 98, 122, 124, and then it goes to 83. So as the algorithm, it is only going to the final request. It is not going to go beyond that. So the variation of C look is, while returning, it is not satisfying any request. But in case of look, it could have satisfied this 37 and then it would have gone to 14. In case of your C look, it is going to go back and it is going to start, and it is not going back till 0. It is only going back till the final request, that is 14 and then 37. So again, let us look into the total number of head movements. In this case is 332. So I have discussed all the algorithms that is a part of your disk scheduling, and these algorithms can be asked as a part of your problem solving. So whenever asked, you're supposed to give this graphical representation and you're supposed to calculate the total head movement. How do you calculate the total head movement? It is very simple. You can see here, you're subtracting from the previous head movements. So and then you summate all that and you get the summation of the total head movements that is taken to satisfy that request. The next thing is where we will see how do we select which is the best scheduling algorithm and which algorithm is best suited for what kind of application and situation. So talking about the selection, we have the SSTF, that is the shortest seek time first. So that is commonly used, and as we have evidently seen, it has a very good performance when compared to all the algorithms. And then talking about your scan and C-scan algorithm, these algorithms are better suited when there is a lot of disk operations, when there are too many access, that is when there are a lot of read and write access that is happening, then probably it is better to use the SAN and scan and C-scan algorithm also has less starvation. than compared to SSTF. Now the selection of the algorithm, it is not only the total number of head count and the performance that we look, there are other factors also that guides the choice. So sometimes if we have to select the disk scheduling algorithm, it could be influenced by the file allocation method as well. If contiguous file allocation method is chosen, then FCFS is best suitable because the files are stored in contiguous blocks and there will be limited head movement that is required. And also, if a linked or indexed file method is used, maybe it is non-contiguous and it is widely scattered on the disk and it has great head movements. In that case, the location of the directories and the index block is also important. Since every file must be opened to be used, and opening the file requires searching the directory structure, the directories used will be frequently accessed. Now suppose that the directory entry is on the first cylinder and the file's data is on the final cylinder. The disk head has to move the entire width of the disk from one end to another end. If the directory entry were in the middle of the cylinder, and the head movement have to move at most half of the width. So caching of the directory and index block in the main memory can also help to reduce the disk arm movement, particularly in the read request. So what happens when we are caching the directory and disk index block? So that reading from the disk is eliminated. We could be directly reading the data. So this is about the selection of the disk scheduling. And to the last, in the disk scheduling, we are only concentrating on the seek time, that is the disk arm movement. Why is rotational latency not considered in the disk scheduling? The one of the things is it is difficult to, so for every read and write request, calculating the disk performance and then calculating the latency and then checking which has the highest latency, lowest latency, that itself can incur quite an amount of time, and that itself can degrade the performance. And second thing, rotational latency is manufacturer specific. That is, one company manufacturer may have a rotational latency that is of 2 milliseconds. The other manufacturer company may have a rotational latency of 2.5 milliseconds, because it is mechanical and it can also get company specific or a manufacturer specific, and that is the reason rotational latency is not considered as a part of your disk scheduling. The next concept that we have is about disk management. Now when we say disk management, other than scheduling, what is that it would need to manage? So we also have to manage the bad boot or the booting of the disk and the initialization of the disk, the bad block recovery. These are some of the responsibility that comes to the operating system as a part of your disk management. So starting with the disk formatting. So a new hard disk, I have told it to you many a times, either it could be a hard disk or your pen drive, that is your SSD, you get it as a blank slate. The platter, if the best example that I could give is, even if the optical disc that you get, that is your CD or your DVD, and you place it for the first time, it is just a blank slate. It just has platters. I mean, the sector division happens only when you format. So it just has the platters on the magnetic recording material, and the process of dividing this disk into sector and filling the disk with special data structure is called the low level formatting. The sector is the smallest unit of area that is read or written by the disk controller. The data structure of the sector typically consists of a header, and the data area is usually 512 bytes in size, and it has a tailer as well. So the data structure contains three things, that is header, data area, and the tailer. The header and the tailer contain information used by the disk controller. It can contain information such as the sector number, the error correcting code. So now, what is this error correcting code? When a controller writes a sector of data during the normal I/O operation, then the error correcting code is updated with the value calculated from all the bytes in the data area. When the sector is read, the error correcting code is recalculated and is compared with the stored value. If the stored value and the calculated number are different, then there indicates a mismatch, that the data area of the sector has become corrupted, and that the disk sector may be treated as bad. So let me just show it. Okay. The operating system needs to record its own data structure on the disk, and this is done in two steps, that is partition and logical formatting. So partition is to partition the disk in two or more groups of cylinders. The operating system can treat each partition as though it were a separate disk, and for instance, one partition can hold the copy of the operating system's executable code, while the other holds the user file. I think that is what we do regularly in your laptops or your PCs. Now your hard disk that is a part of your laptop is 1 terabyte. That hard disk is partitioned into multiple partitions, and you can logically see that each partition will be acting as a disk. So one of those partition is where you have your OS, or you have your operating system that is running, and that is vulnerable. If I say it is your C drive, and again when you reinstall your operating system, there are chances that partition shall be cleared. The next thing that we have is about your logical formatting. So the operating system stores the initial file system data structure on the disk, and these data structure may include your maps of free and allocated space and initially an empty directory. And these are some things about your file system which we have addressed to in your previous module, that is your FAT, that is your file allocation table. So all this could be a part of your logical formatting. So to increase the efficiency, most file system group blocks together into a large chunk, frequently called the cluster. So talking about the boot block, whenever a system is started or it is booted, it must run a bootstrap program, and we have discussed in detail about your bootstrap program in the introduction classes. So what does the bootstrap program do? It basically initializes the CPU registers, device controllers, memory, and then it starts the operating system. For most computers, the bootstrap program is stored in the in your ROM, that is your read-only memory. The problem here is to change the bootstrap code, the ROM hardware chip has to be changed. So to solve the issue, what was done is, so to store this bootstrap, that is to store this tiny bootstrap loader program in the boot ROM. So the job of the boot ROM is to bring in the full bootstrap program from the disk. So previously the whole bootstrap program was on the ROM. Now we are keeping only the loader on the ROM, whereas the program will be stored on the disk. So this loader is going to load the program from the disk. The full bootstrap program now can be changed easily, and it can be written from the disk. So the bootstrap program that is stored is called the boot block, and this is at a fixed location on the disk. A disk that has a boot partition is called the boot disk or the system disk. We can see a small illustration here. So in case of Windows 2000, the system places its boot code in the first sector of the hard disk, and this sector is called the MBR, that is master boot record. The code directs the system to read the boot code from the MBR. In addition to containing the boot code, the MBR also contains a table listing the partitions for the hard disk and a flag indicating which partition on the system it is booted from. So this is about the concept of your boot block. The next concept we have with respect to your disk management is about your bad blocks. Now, what is a bad block? It is an area in the disk which is no longer suitable for storage, or we can say that that particular sector is completely damaged or corrupted. Now, how does this damage occur? We have seen to the structure, the internal of the hard disk, and this hard disk has mechanical movements and it has moving parts, and because of this it is very much vulnerable to failure. In case when the failure is complete, then the disk needs to be replaced and its content restored from the backup media to the new disk. One or more sectors can be defective. More disks even come from the factory itself with the name bad blocks. Now let us see what are the ways that we could be handling the bad blocks. One simple strategy is to do it manually, where we scan the disk to find bad blocks while the disks are being formatted. Any bad block that are discovered are flagged as unusable, so that the file system does not allocate them. If the block go bad during a normal operation, then a special program should be run manually to search the bad blocks and lock them. So that is where we are masking the bad blocks. We are masking the bad blocks so the file system does not make an access to that. The other method that we could do to handle the bad block is the sector sparing or forwarding. So this is a more sophisticated way of handling it. So it works along with the controller, that is the hard disk controller. The controller is going to maintain a list of bad blocks. The list formed by the controller is initialized during the formatting. So this is done at the manufacturer level itself. So it is formatted at the factory and it is updated over the life of the disk. Now the formatting holds these spare sectors which are not at all visible to the operating system. So this task is done by the controller, which will replace each bad sector with a logical spare sector. So this mechanism is known as the sector sparing or forwarding. So as mentioned earlier, there can be a defective disk or sector that can come from the factory itself. So what we do is, at that point of the time, we can identify a list of sectors that has bad blocks, and again we are not allowing the file system to use it. We are giving a spare sector. Anyone trying to access that will be replaced with a spare sector. To give an example how sector sparing or forwarding works, if the operating system tries to read, let me say for example, block number 60, the controller finds that particular sector is bad and it reports it to the operating system. Next time the system is rebooted, a special command is run to tell the controller to replace the bad sector with a spare sector. After that, whenever the system requests the logical block number 60, the request is translated into the replacement sector or the spare address by the controller. The other alternative we have to handle the bad blocks is sector slipping. Some controllers use sector sparing. The other technique also that is available is sector slipping. Now what happens in sector slipping? Let me just narrate it with an example. Now for example, if we have a logical block number 17 that becomes defective and the first available spare follows to sector number 202. Then the sector slipping remaps all the sectors from 17 to 202, moving them all down by one spot. That is, sector 202 is copied into the spare, and then sector 201 into 202, and then 200 into 201, and so on until 18 is copied to the sector 19. So here we are slipping a sector in this way, freeing up the space of sector 18. So sector 17 can be mapped into. So this is about your sector slipping. These are the ways in which the bad blocks can be handled. The next concept that we have is about your swap space management. We have already seen the technique of swapping and the importance of swapping when we have discussed about your virtual memory and virtual memory management. Now, why do we need this virtual memory? We have discussed the importance of virtual memory earlier. Let me just revisit the same. Now, if a computer has sufficient amount of physical memory, but most of the times it is not true, it would need more amount of the main memory. So we swap some memory onto the disk. So the swap space is a space on the hard disk which is a substitute of the physical memory. It is used as a virtual memory which contains the process memory image. Whenever the computer runs short of the physical memory, it uses this virtual memory and stores the information in memory on the disk. Now the swap space helps the computer and OS. It is going to pretend that the RAM is much more, and I have addressed to that in your virtual memory management. So in reality we do not have that sufficient memory. We create an illusion that the RAM is large enough to accommodate that process. Now here this can be called as a swap file. This interchanges the data between the virtual memory and the real memory is called swapping, and the space on the disk has the swap space. So virtual memory is a combination of the RAM and the disk space that is running a processes can use. Now the swap space is a portion of virtual memory that is there on the hard disk, used when the RAM is full. This swap space can be useful to the system in various ways, and it is very essential to manage this swap space. Now, how do we manage the swap space? So, one technique to manage the swap space is using the swap map. Now, the swap area may either be a swap file or a regular file system or a swap partition. Now let me say each swap area consists a series of 4 KB page slots which is used to hold the swapped pages. Now associated with this swap area is the swap map. It is an array of integer counters, each corresponding to a page slot in the swap area. Now, if the value of the counter is 0, the corresponding page slot is available. If the value is greater than 0, it indicates that the page slot is occupied by the swapped page. The value of the counter indicates the number of mapping to the swapped page. For example, here we can see here the counter value is 3. That indicates that the swap page is mapped to 3 different processes. So this is one of the ways how the swap area or the swap space is managed. So that is about your disk management, and your mass storage has a part of your curriculum in module 5. The next chapter that we have is about protection. During the introduction sessions, I have told you the difference between protection and security. Protection is something internal and security is something to external. Now, talking technically, protection controls access to the system resources by programs, process or users. Protection ensures that only the process that have gained proper authorization from OS can operate on the memory segment, CPU and other resources. Protection must provide a means for specifying the control to be imposed, and there should be a means for enforcing the controls as well. As I told you in the start, protection is an internal problem, but whereas security must consider both the computer system and the environment in which the system is used, that is something external. So the difference between protection and security. Now the security must ensure the authentication of the system user and the integrity of the information, the physical resources of the computer system. When we talk about security, it must prevent accidental deletions or unauthorized access, alteration of the data. All this shall be taken care by security. Now, talking about protection, what are the goals, what are the principles, and how protection could be implemented. Talking about goals of protection. Now, the OS contains various objects, hardware or software. So each object have its own operations to perform. Now what does protection do? The protection must ensure that only an authorized process or processes can operate on that particular collection. Protection, why is protection required? Protection is required to prevent mischievous, intentional or unintentional violation of an access. Now, talking about the goals, we have the mechanism and the policies that needs to be followed. Mechanism and policy are two different things. Mechanism determines how something is done. Policies decides what will be done. To give you a simple example, now I am conducting a class on a particular platform is a mechanism. But whereas policy tells I will be conducting this class only for 50 minutes, I am supposed to conduct this class on my given schedule. The mechanism may change, the policy may change, but the mechanism shall never change. That is, the policy today, if it tells the class has to be conducted for 50 minutes, later it may tell the class needs to be conducted for 1 hour 20 minutes. But the mechanism will still remain the same. Having spoke about that, now let us see the principles of protection. So, principles of protection is guided by a thumb rule of least privilege. Now, why and what is this least privilege? Least privilege tells a program, user or even a system are given just enough privileges to perform its task. It goes with an assumption that lesser the privilege, it is also going to lessen the damages, or it is also going to lesser the violations. This principle of least privilege will help us provide more secure computing environment. And also the operating system provides a mechanism to enable the privileges when they are needed, and it disables the privileges when they are not needed. So it is able to switch through this privileges. So further we will be seeing what is the domain protection and what are the various access methods, and we will map it to the matrix.